Hello, friends. This is Jim here with Science Talk. And today I kind of want to do this video explaining how the ocean heat is impacting the ice shelves of Antarctica. So think of this as an explanation of the mechanisms of for the recent videos I have posted where I was discussing the risk that the Rowan and the Filchner ice shelves are facing at the moment, namely that they are in danger of going away. So, a little bit of a background here. So, we were looking at a diagram of the Southern Ocean, and this white contour that we see here. You can see there's a couple arrows there indicating the direction of flow. That represents the Antarctic Circumpolar current, a surface current. And at this location here, you know, there's indicating 160 spheredrups, which is 5 times a larger flow than the Gulf Stream. Well, a little caveat to that. The Gulf Stream, as it's flowing off the eastern seaboard of North America, is indeed flowing at about 32 spheredrops, but it does pick up its flow rate when it gets to about the maritime provinces off to Labrador, Newfoundland, out that direction, where it can reach over 100 spheredrops. Now remember, spheredrops is simply a measure of volume. One spheredrop is 1 million cubic meters per second. So in other words, you're at a location, and every second, 1 million cubic meters of seawater flow past. It doesn't tell you what the velocity is. You could have something that's very, very wide and deep, so it'll be flowing along at a slow rate, or you can have something very narrow, and it'll be really, tooting along pretty quickly. Another thing to keep in mind is when you go through the Drake Strait here between the southern tip of South America and the northern tip of the Antarctic Peninsula, it gets up to over 175, over 180 spheredrops because the current really gets squeezed there, as is indicated here. We can see a narrowing of the Antarctic Circumpolar current. So this is supposed to represent how wide and narrow it can be. This little narrowing here is due to topographic steering, but right through here is where it gets pretty moving along. The volume, that is, can move along rather quickly. And here you can see where it spreads out, so it would kind of slow down a bit. But this gives you an idea of the Antarctic Circumpolar current, and I'll be discussing some features here on the Antarctic Peninsula, Antarctic continent itself. Okay, so you can see you got the Weddell Gyre and the Ross Gyre, from the Ross Sea and the Weddell Sea, and so forth. You got the Amundsen Sea. So, thing to keep in mind here, and on my next video, I'm going to be discussing water masses of the oceans with an emphasis on the Atlantic. But so I will discuss that in more detail. But what this is showing here is that we have a surface current indicated in this, I guess, reddish color. That's the Antarctic Circumpolar current. We see these purple regions where deep water formation takes place. So you got one here in the North Atlantic. This is off Antarctica itself. And then sometimes the water upwells in the Pacific and dives back down. Same thing in the Indian Ocean. This is contributions from the Labrador Sea. This blue here, that's what we're going to be discussing in this video here. That's your circumpolar deep water. And deep water is indicated in blue here. But what you want to take away from this, and I'll go into this more detail in my next video, what you want to take away from this is that think of this as a rotating hub where water masses move off of and move into, pulls it in, throws it out. Big rotating hub that kind of connects all the major water masses of the oceans. Okay, so again, I'm going to be showing these in the water mass uh, video that's upcoming, but this is just to kind of give you an orientation. NADW is North Atlantic deep water flowing in this way. So the North Pole is on the left side, South Pole is over here on the right side of this graphic. AABW is Antarctic bottom water. It's very cold, very salty water, so it just goes straight to the bottom, hence the name. Then we have the AAIW, Antarctic intermediate water, which flows at, not surprising, intermediate depths. So what's this section right here? And, for that matter, meeting up with this section here. Well, as you probably might have surmised, this is your circumpolar deep water. A couple other interesting things here. You have subtropical convergence mentioned here in the northern hemisphere and the southern hemisphere. That's because the middle of the oceans tend to have converging gyres in the middle. And you can see these little arrows here. That indicates the downwelling that takes place in the middle of the gyres. So basically, this is where the gyres are. The equator there. Antarctic polar frontal zone and the Antarctic divergence, where some of the upwelling water upwells, and so water separates. That brings in nutrients. The North Atlantic deep water joins in this and brings up nutrients. And that drives the ecosystem there. So we're seeing basically O2 minimum. Keep that in mind. We're seeing where the circumpolar deep water would be indicated. And this is kind of more of a 3D aspect for you. So again, we see similar things here, but now we're seeing a little separation here, and I'm going to explain what that is in a moment. But it's all part of the circumpolar deep water. So again, Antarctic bottom water, North Atlantic deep water. Okay, here we see the Mediterranean outflow water, and this little arrow is going this direction. That's what brings the warm water to Fram Strait. And we got a couple of, the yellowish are the fronts. Okay, and we have some divergence going on, indicated with this, I guess, orangey color. Okay? And they indicate some of the surface water, 36.5 practical salinity unit, 25 degrees C. So it's very salty, but it's warm, which is why it only sinks to intermediary depths. I'm talking about the Mediterranean outflow water. You can look at the North Atlantic deep water, 34.9 salinity, not as salty as the Mediterranean, but considerably colder, so it makes it more dense and it sinks down. And you can see very similar characteristics as part of the circumpolar deep water. Very cold Antarctic bottom water, that's why it sinks. So you get the idea that the density of seawater is determined by its salt content, salinity, and its temperature, and how they interact will determine its density, how the water will sink and find its buoyancy level. This is kind of a 3D representation. Another 3D representation, and now we're seeing that the Antarctic circumpolar water is actually being identified. There's the Mediterranean water, Antarctic intermediate water with the North Atlantic bottom water sliding underneath that, and of course underneath it all, the Antarctic bottom water. Okay. And we can see we have some spin-off eddies from where the deep water meets the Antarctic bottom water. And we can see the indication for the Antarctic circumpolar current, east wind drift. So kind of have like a little bit of a countercurrent here. There's also going to be Ekman on shore and offshore transport as well. So this is to show you, the divergence, the polar front, because on this side we get on the subantarctic, on this side is more the Antarctic region. And that's defined by the physics. And so now to tell you what we've been looking at, especially here and here, we're looking at the upper circumpolar deep water, and they should probably put an L here for the lower circumpolar deep water. And there's the Antarctic bottom water, Antarctic intermediate water, and this is the South Atlantic modified water. This is the South Atlantic front, the polar front, etc. The North Atlantic deep water is not indicated on this diagram. And you get an idea of the depth going down to basically 4 kilometers. And here's a 3D representation. Again, we're seeing the Antarctic bottom water in the dark blue. You can follow the flow this way. We see the lower circumpolar deep water, the upper circumpolar deep water, and you notice how the North Atlantic deep water is wedging its way in between these two. And of course, the Antarctic intermediate water is found over the top of all of them. And these kind of represent the approximate relative thicknesses. This yellow arrow here is the Antarctic circumpolar current moving in this direction. There's your polar front. You have the Antarctic, subantarctic. And then you see this here, the arrow's moving this way. That's all part of the divergence. So just to kind of help you visualize some of the water masses involved, and I'm gonna be basically looking at the circumpolar deep water. Okay. Now look at Antarctica here. And we see the Antarctic Peninsula jutting out considerably into the Southern Ocean. The southern tip of South America will be over here about. And we have the Ross Sea with the Ross Ice Shelf. And near the Ross Ice Shelf is the McMurdo base operated by the U.S. Here's the Amundsen Sea right over here. It's not indicated on this diagram, but in this region is where you find the Thwaites and Pine Island glaciers, which feed into Pine Island Bay, which adjoins the Amundsen Sea. Pine Island Bay is right in here. So here is where people, colloquially refer to Thwaites as the Doomsday Glacier, but this is where it's found, right in here. Thwaites and then the Pine Island Glacier right next to each other. There's scientists saying that that's in danger of collapsing, and that would contribute significantly to sea level rise. And here is in the Weddell Sea is the Rhone ice shelf, and right next to it on the other side of this little bit of land is the Filchner ice shelf. So you can see why they kind of collectively put it together at the Filchner-Rhone ice shelf. But this is what I was discussing in my previous videos. This right here. This is what scientists are having concerns about. There's the Rhone ice shelf. Here's the Filchner ice shelf. And up over here is the Larsen ice shelf. So you got the Larsen, Rhone, Filchner, Thwaites and Pine Island glaciers here, and the Ross ice shelf. So, and of course, you got all the ice over on the continent itself. So here are some of the major ice shelves that have been gaining a lot of attention among researchers and in the news in the recent days and recent years. Okay, so let's look at some diagrammatic representations of what is meant by an ice shelf. Ice shelf, the important thing to remember is that ice shelf is ice that is derived from the land, not the sea. You do have sea ice, but that's out here. Okay, so think of this as a big old glacier. So we're on the land here, and then we have a feature called the grounding line. The grounding line is where it's land, and that is land that the ice is in contact with. Beyond the grounding line, as we can see here, we start seeing oceanic water. This is what is the start of the ice shelf. So the ice shelf is, in essence, think of it as being cantilevered past the grounding line. So this is just, it's still attached to the land ice, but you have water underneath it. So it's kind of sitting there on top of the water. And the ice continues to flow this way. Obviously, the ice front is where the ice shelf ends and meets the seawater, the interface there. We see some ocean currents that can work its way in. This is showing the same thing here. Again, we have the grounding line. Then past that, it's cantilevered past, crevasses, some cracks in the ice. Okay. Cabbed icebergs, you get the crevasse, they break off, right? And you get little icebergs. Sea ice formation. That is a different source than ice from the land. Right? That's when the sea itself freezes. You get brine rejection. Right? You get a little bit of vertical flow because you have very salty water at the surface, and it sinks down because it's more dense. Now look at this red arrow. Right? That represents the warm circumpolar deep water that flows in under the ice shelf. Now, as I'll explain later on, this is actually the upper circumpolar deep water. So we get this warmer water flowing in, it starts melting and melting under the ice shelf. And they're using this to indicate Thwaites Glacier. But again, we're seeing the same thing. We have the grounding line, we have a cantilever path, we have again the circumpolar deep water flowing in. You have some high salinity shelf water. You might have a buoyant melt plume because it's warmer, so it starts rising. This little red arrow that you see here is the heat from this water moving up to the surface to either melt the ice and or flux to the atmosphere, diffuse to the atmosphere. Here's the indication of the Antarctic circumpolar current moving this way. You have some sea ice here, and obviously in the Munson Sea. So hopefully this clarifies, because I received some comments and questions that there might have been some confusion on what is an ice shelf. Ice shelf is land-derived ice. It is not sea ice. So if the ice shelf breaks off, yeah, it melts, it will add to sea level rise. When sea ice melts, there's no change in sea ice in sea level because, well, the ice was originally from the water to begin with. But when you add the ice from the land and that melts, yes, then sea levels will rise. That's why we're so worried about these ice shelves, because these things break off and get into warmer, lower latitude. They will melt and sea levels will go up. And here's Pine Island, right? Showing the same thing again. We're seeing the influx of the circumpolar deep water and how it's causing the melting. This is the ROV. This is what I was trying to discuss and convey in my prior videos. That they're sending in these unmanned instruments, and they're measuring and they're finding that this circumpolar deep water is infiltrating, moving in about 18 kilometers to the underside of the ice and melting it from there. As if we didn't know that was a ship. But anyway, and then here's a really uh, large view. We can see, some of the going up the continental shelf, the continental slope. We've got some warm, uh, deep water here. We've got some you know, deep, cold, deep water, Antarctic bottom water. We got some shelf water. But here is the Rhone ice shelf. Here is the Filchner ice shelf. Hey, Larsen is over here. There's the Ross Sea, the Munson Sea. So this is where, and there's Pine Island Bay. This is where we're going to find Thwaites and Pine Island glaciers right here. So when you really come down to it, all of the focus is on West Antarctica because you have the Transantarctic mountain chain here. So we're all looking at stuff on the west side of the Antarctic continent, and that's where the ice shelves are of interest to us. And it says here, the Antarctic ice sheet does not completely rest on solid ground. It's right. That's what I'm talking about. The cantilevering past the grounding line. At the coast, it forms permanent floating sheets of ice, which are still connected to the land mass, or the mass of ice on the over the land, and cover 10,000 of square kilometers. These giant floating ice tongues are called the ice shelves. They prevent the huge amount of inland ice from quickly flowing into the ocean. However, as it gets warmer, the ice shelf may no longer serve as a buttress to the flow of grounded ice. Since less and less sea ice is forming, the water density on the continental shelf will decrease, thus allowing warm water to flow underneath the ice shelf and melt it from below. Now, when you form sea ice, as the oceans freeze, you have brine rejection. It kicks out the salt. That makes the salt, that makes the salinity increase, making the water at the surface dense, and it sinks. Well, if we're losing the sea ice, we're not going to have that mechanism. We're not going to have that, you know, dense water at the top there. So you're going to allow the warmer water to infiltrate. And here's another thing to keep in mind. Okay, let's go back up a slide or so. Okay, when we have sea ice here, okay, the sea ice, of course, depending on the time of year, can get really thick and extensive. And it's oftentimes you won't know where the shelf ice ends and the sea ice begins because it's just slammed up against each other. And of course, a lot of that depends on wind action blowing in the correct way and the physical movement of the water underneath. But when you also have that sea ice slamming against the ice shelf, that is a further buttressing to prevent any more inland ice from galloping out into the ocean. So the presence of sea ice is also important. And as we're seeing now, we're seeing the data showing that the sea ice around Antarctica is basically setting record lows, just like in the Arctic. Okay, so what's going to happen with the future path of the heat? Well, the next slide will do a little zoom in on these two figures here. And basically, here's the sea ice. You can see how they're representing the sea ice buttressing up against the ice shelf. You can clearly see how it's cantilevered past the grounding line. Right? Here's some movement of warm water. Well, we're losing the sea ice, and now we see the infiltration of the warm water getting underneath the ice. And it's warm. It starts melting it from below. You notice that in the diagram, they're representing less amount of sea ice. So that's another concern, as I just discussed. So that is the mechanism. That is what's going on. So you have the ice shelf cantilever path. You got this warmer water now starting to make its way in, melting the ice from below. Coupled with warmer air temperatures melting the ice from above. And you can see how the ice shelves are at risk. Okay, some comments here, a little further explanation. Circumpolar deep water, CDW, is a designation given to the water mass in the Pacific and Indian Ocean, basically the source of it, if you will. That is a mixing of other water masses in the region. It is characteristically warmer and saltier than the surrounding water masses, and this causes the circumpolar deep water to contribute to the melting of ice shelves in the Antarctic region. Okay, and of course, there'll be little fine tuning of that. Circumpolar deep water, the greatest volume water mass in the Southern Ocean, includes the combination of the North Atlantic deep water, NADW, Antarctic bottom water, AABW, Antarctic intermediate water, AAIW, as well as recirculated deep water from the Indian Ocean and Pacific Oceans. An unusual characteristic of the circumpolar deep water is that the water is not formed at the surface. Usually, most deep water forms at the surface. It gets, for whatever mechanism, it gets very dense and it sinks. Rather, this is simply a blending of other water masses. And it sits at a depth of around 500 meters once it encounters the NADW. And that's about, the depth of the continental shelf. So, in the previous slide right here, get up there, I said it's a combination of the Pacific and Indian Oceans. In these locations, it is quite deep. As it moves and starts interacting with these other water masses, we find that it shoals upward. Okay, so there are two types of the circumpolar deep water, the upper and the lower. The UCDW is what originates in the Indian and Pacific Oceans. It has the warmer temperatures and the lower oxygen levels. You might recall in the earlier graphic there was minimum O2 indicated. That's what that was getting at. The lower is colder. The lower comes from the NADW, has a higher salinity. In the Indian Ocean, the deep water has a temperature about 1 to 2 C. In the Pacific, it is slightly colder with a temperature of 0.1 to 2 C. The salinity of the CDW is 34.62 to 34.73 PSU. That's practical salinity units. North Atlantic deep water is more dense than the upper circumpolar deep water, pushing the upper circumpolar deep water above the NADW, causing the upper to shoal to more intermediate depths, which gets back to this 500-meter statement there. Okay. CDW in the Pacific and Indian Oceans are dense enough such that the water mass is found at deep depths. However, as it encounters the NADW and the AABW, it is less dense and shoals upward to more intermediate depth. I'm just driving home that point, forming the upper UCDW and leaving behind the lower CDW. When the UCDW flows upward onto the continental shelf and travels through the deep canyons, it reaches the underside of the ice shelves. The warmer water makes contact with the shelves, contributing to the ice shelf melting, and before that, sea ice melt. Okay? So it contributes to the ice shelf melting and subsequent sea level rise. The Pacific Ocean has absorbed an enormous amount of heat energy. This heat energy is expansive and penetrates deep in the water column. Recall my ocean heat content update video where I showed you that big blob in the North Pacific. This heat energy is what is contributing to the warming of the CDW, later becoming the new CDW. It is this heat energy that is contributing to the melting of the various ice shelves around Antarctica. It is this heat energy that is now accelerating the melting of the various ice shelves around Antarctica, for example, Filchner-Ronne, Pine Island, Thwaites, and causing as well, in addition to increasing the melting of these ice shelves, causing these ice shelves to lose a lot of their mass, it's also increasing the loss of the sea ice as well. So we're warming the ocean. The ocean has absorbed a lot of energy, and that extra energy is accelerating the melting. This is why researchers are concerned that we may be losing these ice shelves. And with that, significant increases in sea level. So, remember, since 1971, the oceans have absorbed about 93% of all heat energy humans have introduced to the atmosphere from the burning of fossil fuels. Of this amount, about 68% are concentrated in the upper 500 to 700 meters of the oceans. As heating and warming of the upper ocean layers continue, any thermohaline flow to sequester heat to depth will decrease. In fact, it already is decreasing. This leads to further increased stratification of the upper layers, further increased warming of these layers. Gas solubility will decrease, leading to gas saturation sooner. And that the result will be that the oceans will no longer be able to absorb CO2 from the atmosphere, and CO2 levels in the oceans will outgas back to the atmosphere, for causing further warming. So, in addition to not only the CO2 reintroducing to the atmosphere, but the heat contained in the ocean will diffuse also to the atmosphere. So you take the CO2 and the heat energy, we'll call latent heat energy, fluxing to the atmosphere, that will increase air temperatures. We're seeing that here in the Arctic. Right? I've covered, I've done a lot of extensive videos. There's more coming, but I've done a lot of extensive videos discussing all that's happening in the Arctic that's now warming 3-4 times, in some places 5 times faster than the rest of the planet. Okay? So all that heat energy in the oceans going to the atmosphere. Right? And along with the CO2 to the methane to the warming of the planet. And with water masses moving about horizontally, that heat will also be distributed around the planet. In other words, from the water itself moving around the various ocean basins, and as it's moving around, it's fluxing heat to the atmosphere. Right, so that heat will be distributed to the planet, around the planet, leading to the mechanisms discussed here. In other words, in addition to fluxing to the atmosphere, we then see more and more heat making its way to the underside of the ice shelves in Antarctica, accelerating the melting from below. To think this heat will not be a factor, it's in the ocean, no big worry, like an out of sight, out of mind mentality, that won't have any impact. Well, that's just being naive. You cannot argue with thermodynamics. You cannot argue with physics. So, if you are interested in further analysis, I've done a whole bunch of videos. Please watch my videos on the ocean heat content. Got 2 of them out there. Also, one on overturn mixing and stratification. I have another one on all about salinity. And any other videos where I discuss all the stuff going on in the Arctic, you can just simply click on the video tab on my page, scroll through there, and click on what interests you. So kind of to recap, it's the increased ocean heat in the oceans. It's making its way to the circumpolar deep water. This increased ocean heat is increasing and accelerating the melting of the ice shelves, imperiling the ice shelves. Okay? 7% is what energy is stayed in the atmosphere. And look what that has done. Now just imagine what this other 93% will do. Well, we're starting to see it. So just because you think the heat's in the low latitude regions of the ocean doesn't mean it's going to stay there. It gets moved around. It moves from pole to pole, equator to pole, mid-latitude to mid-latitude. It gets moved around, and now we have this extra warmth of the Pacific and Indian Ocean, increasing the temperature of the upper circumpolar deep water. That extra heat, and more of it coming all the time, makes its way under the ice shelves, melts the ice shelves from below. That is accelerating. That is imperiling the ice shelf, and you get big, massive slabs breaking off. Eventually, they will make its way to lower latitudes where they will melt and contribute significantly to sea level rise. So, I just wanted to put this video quickly together for you to explain what is going on. And there you have it. We see similar mechanisms in the Arctic. Of course, Arctic is sea ice alone because, it's the ocean there. But we still see what? We have warm water being advected in, melts the sea ice from below. Well, here we have warm water in Antarctica being advected in, melting the shelf ice and sea ice from below. So there you have it. If you found this video informative, please give it a thumbs up. Please subscribe if you have not done so already. And please share the video, this and my other videos, on the social media platforms that you utilize. I hope if you are not already a patron of mine on Patreon, I hope you will consider supporting the work I do by becoming a patron at patreon.com. You can find the details in the description box below the video. Thank you for your time, and we'll talk soon.